Okay, in this video we're going to look at the three basic electrical properties. These are properties that we're going to talk about a lot over the next couple of weeks. They are voltage, the current, and the resistance. And each of them plays a different role in terms of what is happening inside of an electrical system. Each of them represents some different aspect of this movement of charges through an electrical system. So let's look at the first one. We've already actually been introduced to this idea of voltage. Just to remind you, voltage is kind of like the nickname. The proper name for the property is called the electric potential difference. So we will always, for this chapter, we'll be referring to this as the voltage, but ultimately it's the same thing as the electric potential difference, and that is that it is the work per unit charge, or more simply, the energy per coulomb of charge. So in other words, for every little package of charge, we send 1 coulomb of charge through the system. For every coulomb that we send through, the voltage is going to tell us how much energy those charges have. And essentially, the entire idea behind the reason why we use electricity at all is because it is a way for you to transfer energy. So this property, the voltage, is incredibly important because ultimately that's the goal for all electrical systems, is to transfer electrical energy from one place to another. Could be, in some cases, miles or even thousands of miles. We transfer the energy to some place where somebody needs to use it, and then they connect their electrical device to it to extract that energy. And these three properties are going to be the central players in most of our calculations on the electrical side. Now, but also we want to be able to connect it to the energy, and that's where voltage is so important. So essentially the voltage is how much energy is going to be transferred by 1 coulomb of charge as it moves through the system, or it could be as it moves through an object like a resistor or a light bulb, for example. So we've already seen the equation for voltage, and that is that V is equal to, now in the past I would have said W over Q, but I really want to open this up a little bit more so that instead of just simply thinking about work, I want to think about all the different kinds of energy. And of course, I'm sure you remember that energy is simply the ability to do work. So it's perfectly fine to replace the letter W, work, with any other form of energy because all forms of energy represent the ability to do work. So this thing has units that we've already talked about, and in this case that was joules per coulomb, and this is referred to as a volt. And the symbol for it is capital V, right? And remember, that's a kind of unusual thing because we haven't really had any other properties where the property letter and the letter that represents the units is actually the same letter. Now, we're not going to talk about this in great detail because we've already discussed it in the previous topic on electrostatics, but let me just remind you the basic idea is that I'm going to connect this to gravity because gravity is something that you have a lot more experience with. I mean, you've seen it over and over and over in your life. And if we were to take a small marble and to raise that marble up here so that it was at the top of this hill or this ramp that I've made, that's the V, that's the voltage. That's how much energy has been given to this object, and it represents some available energy, some energy that is potentially available to be released. As the object moves down this way, so we raise the electric potential up, as the object begins to then move down, we transform from potential to some form of energy. Now that form of energy, there's lots of different forms, but the two main ones that we're going to look at in this chapter are going to be light and also heat. Now, they can be used for all kinds of things. Your computer uses electrical energy, and it does that to make calculations, and it also produces light, it also produces sound. There's lots of things that it can be used for, but essentially by raising up this marble, we increase its gravitational potential energy. That's the same thing that the battery is going to do. The battery is going to increase the potential energy, the electrical potential energy of the charges that pass through it. So voltage is something we've already kind of talked about. The one thing I want to really stress before we move on to the next property is the idea that voltage represents energy. It is what is driving the system. The voltage only arises if you have an electric field. So if, for example, we were to draw a uniform electric field, so perhaps this is like inside of a wire. What makes the electricity in a wire moves is that there's an electric field. If there is no electric field, then there is no movement of the charges. So if we assume that we have a small positive charge here, this distance across here represents some potential change in energy. So if we allow this electric potential to do what it wants to do, which is to drive this charge forward, then it will begin to move through this. And as it encounters this thing called resistance, some of that energy will be extracted. Now, there's a couple different things to think about. Besides how much energy the charges have, obviously how much energy gets delivered to this side of the system is going to depend a lot on how many charges move. So these guys may have a large voltage, like maybe 12 volts, but if there's only a small number of them, then you're not really transferring that much energy. So the amount of charge that moves is really important in terms of thinking about how much energy did I really transfer? How much energy is being delivered from the electrical system to the thing that you're trying to deliver it to? And so that's why electric current is also an equally important property to voltage. While it does not measure how much energy is in the system, it does tell you how much charge is passing a point every second. So the letter for it is the letter I. You can use lowercase I, although generally speaking, you'll probably find that it's capital I. It says the amount of charge. Charge is represented by the letter Q. And then this is how much is passing per second. So that means that we are measuring how much time has gone by. Now, these guys also have new units to think about. Now, the units for charge and time, those are old units, but combining them together is going to create this new unit. So this is a coulomb per second, and a coulomb per second is called an amp. Okay, that's actually short for amperes. It's the name of one of the early kind of pioneers of electrical systems, and just really played a really crucial role in just helping our understanding of how electrical systems work. And the unit for current is named after him. The symbol for it is capital A. So this is more typical, where the letter for the property and the letter for the unit, the two different letters. It's confusing sometimes to have the same two, the unit and the property actually have the same letter. It does create a little bit of confusion. So fortunately, we just have the one for voltage, where we really need to worry about it. Now, obviously, just to make this more clear, the current, even though it's measured in amps, in your mind, I really think it's important for you to understand what is the amp telling you? What is the secret units that it's hiding? So if, for example, I said that in a particular circuit I had 5.0 amps, what that would tell me is that 5.0 coulombs per second were traveling through the system. Now, you won't see a lot of problems like this. Ultimately, mostly this version of the equation, we won't use it a lot. We're not going to be super concerned about specifically how much charge has passed through the system. We're really going to be much more concerned with how much energy has passed through the system. So while this is the definition of current, you'll see that in the next equation that I'm about to give you, you're going to use the next equation much more often than this. Really only at level 1 will you probably even see this equation. Then once we get off of level 1, you will still be required to know what current is, but we will have new equations that also take advantage of this property called current. So that brings us to the last of the three major electrical properties, and that is this thing called the resistance. Now, voltage and current, neither one of these things are things that were discovered. Nobody discovered current. They just needed a way to describe it. It's similar to, like the color red. We didn't discover the color red. It was always there. It was always apparent. It's just that we gave a label to it. We gave a name to it so that we could all talk together. And so we'd have some kind of common language. And similarly, the voltage and the current are like that, in that they are properties that are just basically made up. We just made up these properties as a way of being able to measure how much energy is in the system or how much charge is moving through the system. And the last thing that we want to know about this electrical system is, how easy is it? Is it easy for the charges to move through the system, or is it really difficult for the charges to move through the system? And so scientists, and especially some of these early pioneers like Coulomb and Ampere, they came up with this idea of resistance. So resistance is a way of putting a number. This is really important. We don't want to just say, well, it's difficult or it's more challenging. No, we want a number. We want a numerical value that will tell us how difficult is it for charge and therefore for energy to move through this electrical system. So the symbol for resistance, this is really easy. It is the letter R. And the definition of resistance is, and this is what scientists decided that they wanted to use for their definition of resistance, it's the ratio of the voltage that we just talked about a moment ago to the amount of current. How much energy is being given to the charges divided by how much charge is actually moving in any given second. So the symbol for the property is capital R, and then we already have the symbols for the previous two, which is V and I. This equation for resistance is so fundamental. We are going to use this equation over and over and over again. Literally dozens of times we're going to make this calculation. Sometimes solving for R, sometimes solving for I, and sometimes solving for V. But this equation for resistance kind of brings together the three major electrical properties. As you can see, there's voltage, there's current, and there's resistance. So it develops a relationship between those two. Now, we'll talk more about this equation in future videos when we talk about Ohm's law, but we don't need to talk about Ohm's law right here because this is the definition of resistance. This is always true. In any circuit, if you take the voltage passing through some object, like let's say a light bulb, and you divide it by the amount of current, that will tell you the resistance of that light bulb no matter what. Now, whether that resistance stays constant or changes, goes up or down, that depends on the object and depends on the circumstances of that particular thing. But it is always true. This is always an equation that can be used, that the resistance is V divided by I. So let's think just for a second about the units for this. This is a new property. On the top for voltage, we have volts as the unit. On the bottom, we have current, which we just talked about is amps. So that's volts per amp. And we call those ohms. So named for another early scientist who did a lot of the pioneering work and understanding electrical systems. Those are called ohms. And the symbol for it, now here's the problem. We do not want to use the letter O as a symbol for a mathematical property or for a property that is quantitative because the O looks like a zero and it's kind of confusing. So instead we use the Greek letter omega, which kind of sounds a little bit like ohms, as the symbol for resistance. Now that's a little bit different. So that's kind of an unusual thing. We're using a Greek letter because there just aren't enough letters in the alphabet, and we definitely don't want to use the letter O as a symbol for a property because the thing right in front of that is going to be a number. So that would be very confusing to say 25 O's. So we say ohms, and we use the symbol omega to represent that guy. Now, before we look at some of the variations of this equation, how would you solve for I? How would you solve for V? Let's just talk about, does it make sense? Does it make sense to use this definition to measure the resistance? Remember, we are trying to develop a numerical system, a system of numbers that will tell you whether the resistance was high or very low. Was it easy for the charges to travel through the system, or was it really difficult for the charges to travel through this system? So let's take a look at two simple examples. So let's say, for example, that you have a very large voltage. Okay, so you're putting a lot of energy into these charges, but you only get a little teeny amount of charge. Very, very small amount of charge goes. Well, let's just think about what's going to happen when I make that calculation. I'm going to have a very large number, and that number is going to be divided by a very small number. So what is the result of that going to be? The result of that is going to be that we are going to get a very large resistance, or a very high resistance. And I'm going to put a number on this resistance. Just to make sure that this is clear, let's actually do a numerical example. So let's say that you have something plugged into the wall outlet where the voltage is 120 volts, but when you measure the amount of current that's passing, you find that you're only getting 0.1 amps, so a very small amount of current. Well, in that case, you have a very large number divided by a very small number, and the result of that is going to be a very large number. So in that electrical system, we would be looking at 1200 ohms, which is not super high resistance, but it's up there. It's definitely a fairly large resistance. So what is the opposite of that? Well, the opposite of that would be to put a very small voltage. So I just barely put in voltage to it at all, but what I find is that I get an enormous amount of current. So now I have a very small number divided by a very large number. That's going to cause the resistance to be lower, or the calculation to be lower. So low resistance. And let's take a look at how that looks. So we said that we were going to have a low voltage. Let's say that in this case we only have 5 volts for the potential, electric potential. But then for the current, we actually get a pretty large amount of current. Let's say we get 2 amps, which is quite a large. That is more than enough to induce a heart attack in people. If you had an amp, more than 1 amp going through you, it would definitely be very dangerous. Actually, even a little lower than that would still be considered to be pretty dangerous. Well, in this case, we would get a resistance of 2.5 ohms, and you can see that's much, much lower. Even though, look, my voltage was very small. I wasn't giving very much energy to these charges, but they were still able to move relatively easily. And I can tell that they moved relatively easily because even though I only gave them a little bit of push, I got 2 amps to move, whereas for the higher resistance one, I gave them a push of 120 volts and I only got 0.1 amps. So it must be very difficult to travel through this system. If I pushed so hard with this much voltage and I only got this little tiny trickle of current. And by contrast, when I put a very small voltage to this other object, I was able to get 2 amps, which is quite a lot of current, and therefore it must have been much easier for the charges to move. And so this is the basic idea of resistance. It does make sense. The resistance will be high when you have a high voltage and a small current because it's difficult. It's difficult to travel through that system. By contrast, with a relatively small voltage, if I were to get a lot of current, that would tell me, oh, this is a very easy circuit to move through. The charges are moving relatively effortless. There's not really that much in their way. Now, we will talk more about resistance. We'll just focus specifically on resistance and the connection to heating, because this resistance that you see, it does cause objects to heat up. They transform some of their energy into thermal energy, and we'll talk about that quite a bit more. The last thing I just want to leave you with is to remind you that while this is the definition of electrical resistance, it's actually used in several other ways. So for example, I could say that V is equal to IR. We're going to use that equation a lot, especially as we get up to the higher levels and we start looking at more complicated circuits like series and parallel circuits. Or I could solve this for I, in which case I would multiply by I, that moves the I up here, that's the V equals IR. And then if I were to divide by R, I would end up with I by itself, and that says that I is equal to V over R. So these are it's the same equation, just it's not a different equation. It's the exact same equation. It's just being used to solve for different properties. So in any electrical property or any electrical object, you can get the voltage by doing I times R, you can get the current by doing V divided by R, or you could get the resistance by doing V divided by I. So every electrical device has some voltage that is applied to it. As a result, some current flows, and we can measure how difficult it is to have that current flow or how much energy is flowing through there by simply using the resistance. So this equation is probably the most important of all the 3 equations because this actually links together all of the 3 basic electrical properties: voltage, current, and resistance. And it is always true. This equation is always valid to use.